Take a lump of metal, thousands of atoms fused into a single grain far too small to see. Now throw it at a wall with two slits cut into it. You already know how this ends. It goes through one slit, or the other, or it bounces off. One object, one path. Every solid thing you have ever held in your hand obeys that rule. In a lab in Vienna, a piece of metal just refused to. It did not choose a slit. The only honest way the physicists can describe what it did is to say it spread out and went through more than one path at the same time. Like a wave, not a photon, not an electron, not a single atom. This was a speck of solid sodium built from more than 7,000 atoms, heavier than almost any protein in your body. And for about 1/100th of a second, it stopped behaving like a thing in one place. Here is what makes that so hard to swallow. Quantum weirdness is supposed to be the rulebook of the very small. Light can act like a wave and like a particle. So can an electron. Fire electrons one at a time through two slits, and they slowly paint a striped pattern on the far side. Bright bands, dark bands. The unmistakable signature of a wave passing through both slits and interfering with itself. Atoms do it too. Then molecules. And every time someone makes the object bigger, the same question comes back. And it has never been answered. Where does this stop? Because something has to give. Your coffee cup does not spread through the doorway like a ripple. Dust does not leave interference stripes on the floor. The everyday world is stubbornly, boringly solid. So a lot of serious physicists have wondered whether quantum mechanics simply runs out of road. Maybe once an object gets heavy enough, the wave nature quietly switches off. Maybe gravity itself reaches in and forces a big object to pick one location and stay there. If any of that is true, then somewhere between a single electron and a grain of sand, the rules should break. So you go looking for the breaking point. You build the heaviest thing you can, and you dare it to behave like a wave. That is exactly what the team around Marcus Arndt and Stefan Gerlich did. They started with sodium, ordinary metal, and grew it into tiny clusters, each one a frozen ball of 5 to 10,000 atoms, chilled to the temperature of liquid nitrogen. Each cluster was about 8 nanometers across. That is close to the size of the smallest features on a modern computer chip, and it carried a mass of more than 170,000 atomic units. In the world of quantum experiments, that is a monster. Now comes the problem. You cannot just watch which way it goes. The instant you measure the path, you destroy the very thing you are testing. Look, and the wave collapses into an ordinary particle. So they never looked at the path. Instead, they sent the clusters through 3 gratings made not of metal, but of standing waves of ultraviolet laser light, bars of light and shadow, spaced 133 nanometers apart, about a meter between each grating, inside a vacuum roughly 100 billion times thinner than the air you are breathing right now. If the clusters were just little pellets, they would cast one kind of shadow through those bars of light. If they were riding a quantum wave, they would build a completely different pattern, sharp, repeating fringes that no classical pellet can make. There was no screen lighting up, no glowing copy of the metal in 2 places. The answer was buried in the numbers, in where thousands of clusters landed, run after run, as the 3rd grating slid slowly across the beam. And the pattern that came out was the quantum one. And there is one number in this experiment that is hard to even picture. A clump of 7,000 atoms has a wave, and that wave is almost impossibly small. Its wavelength was around 10 to 20 femtometers. That is smaller than a single atom. It is down near the size of an atomic nucleus. They pulled an interference pattern out of a wave that tiny, riding on a lump of metal. And to do it, the cluster's position had to be smeared out, delocalized, across a region more than 10 times wider than the cluster itself. That is the heart of it. For that stretch of flight, the metal was not a dot following a hidden route the scientists failed to track. Its possible paths were one single, spread-out quantum state. A solid object, in a blur of places at once. Now, a careful skeptic should push back here. Classical physics can fake stripes. Shadows make bands. Simple optics make patterns. Seeing lines is not proof. The team knew that. So they did something the fakes cannot survive. They turned the middle grating up and down, changing the strength of that wall of light, and watched how the pattern answered. A dumb classical shadow and a real quantum wave respond to that knob in completely different ways. They split apart, and the data followed the quantum curve, right where the two predictions part company. There is even a score for how far into quantum territory this pushes. Physicists rank these experiments on a scale they call macroscopicity, basically how hard you are squeezing the idea that quantum rules might quietly fail at large size. This result scored 15.5. The previous record sat about 10 times lower. In one experiment, Vienna moved the frontier by a full order of magnitude. Which brings us straight back to the breaking point. The theories that say quantum mechanics has a hidden size limit make a clean prediction. Take an object this heavy, let it travel this far, and the wave should fade. The fringes should wash out on their own. Collapse should win. It didn't. The metal kept its wave. No new physics needed. No secret cutoff. At least, not here. So why does the world around you look so solid? The leading answer is almost more disturbing than collapse. The everyday world is constantly being measured by itself. Air molecules slam into things. Heat leaks out. Light scatters off every surface. Each one of those tiny interactions is a measurement, and measurement is exactly what crushes a quantum wave down into a single, definite thing. The universe is watching everything, all the time. And that relentless watching is what keeps your coffee cup in one place. But that still does not give us the final answer. Does quantum mechanics actually hold all the way up, with the environment just hiding it from us? Or is there a real edge out there, waiting at some heavier mass, where the equations finally crack? The only way to find out is to keep climbing. Heavier objects, quieter machines, longer flights. The Vienna group has already said they want to beat their own record by orders of magnitude. Atom by atom, cluster by cluster, they drag the boundary upward and ask the same question every single time. Does quantum mechanics still survive here? So far, every time we have asked, the answer has been yes. And maybe that is the part worth sitting with. The strange thing was never that a lump of metal can act like a wave. The strange thing is that everything else, your hands, this room, the whole solid world, somehow manages to look normal. There are a few books in the description if you want to go deeper into the kind of physics we explore on this channel. And if you want to keep going right now, there are 2 videos on the end screen that connect with the bigger questions we keep coming back to here. Thanks for watching. See you in the next one.